Thank you. Thank you for inviting me today to share our work, LLM-Rec. So I'm Hanjia, a third-year PhD student at the University of Rochester, and this work was done during my internship this summer at Meta. So as you can see that the idea of our work is quite simple, that we want to improve personalized recommendation by prompting large language models. And let's see. So the problem that we want to address is the issue that we have observed in text-based recommendation systems. Because I think text-based recommendation system has a wide applicability in almost every area, because the capability of natural language to effectively describe almost any type of items, including short videos, movies, products, and foods or recipes. But there are still some challenges in describing items in nowadays real scenarios, because the item description could be incomplete or insufficient. There may be insufficient information, and that can stem from mainly two sources. One is that we do not have a full comprehension of the items that we want to describe. Then we may miss some important information regarding these items. And another is that just imagine this scenario that you want to recommend some items to some people. You can recommend it by just describing the item characteristics itself, but also, let's say if you know that this person is more into some specific types of properties that this item could hold, then you probably can highlight those characteristics of this item. So a second source of this incomplete or insufficient information that we observe is from the insufficient understanding of the users that we want to recommend our products or items to. And this incompleteness doesn't only come from some well-defined or categorized items, such as movies. As we know that movies, they are well classified. They have genres to be categorized. They have main actors. They have maybe country information. So we know that these types of items, like movies, they are well categorized. But nowadays, we do not only want our recommendation system to be applied in these well-classified areas. We also want to extend it to some domains that are more novel or unclassified or less categorically structured items, such as the user-generated content. There are a lot of examples. For say, the short videos on short video platforms, most of them are user-generated and they are dynamic. You may see some patterns among these items, but they're relatively new. It is not like a movie that you can construct a knowledge graph or a well-constructed knowledge base to understand this item, because these short videos, they come in a very short time, short period. So this is the whole motivation that we have observed, or what we have for our framework. And so given this observation, we did some like simple trials that because I was doing the internship while we were preparing for this framework at Meta. So it naturally came to me that how about that we try some like real products So I opened my my own phone and I turned on IG Reels and I just browse randomly about the short videos. And then I try to type some of the video caption into ChatGPT, and I ask that a video caption is this, like gardening with pugs, oof, hashtag gardening problems, hashtag Pugdashians. Then, because at that time I was only playing this thing with ChatGPT, more specifically 3.5. So I wasn't inputting any visual information by that time. But still, you can observe very like amazing ability of ChatGPT of enriching this, maybe you can consider as incomplete or insufficient item description. The most a surprising part of this explanation is the one that I highlight here, is that when I first saw this hashtag Pugdashian, I didn't connect it to Pug or Kardashian. I was just thinking, okay, this might be a newly made hashtags. But as you can see here, ChatGPT was able to tell that this hashtag Pugdashian is a play on words, likely referring to the popular reality show and the pug. And this indicates a humorous comparison or reference. So as you can see that sometimes, especially for these user-generated items, if you want to fully understand these item descriptions so you can make good recommendations, you may need some well-prepared context. Say you need to know there is a TV show, and then you need to understand that this is a play on word. So in another word, you have to be very knowledgeable. You have to be an expert. But now that we have ChatGPT to serve at that role, so this is the motivation here, that we want to leverage ChatGPT or these large language models to enrich the original item description. And the framework is very simple, because you don't need, or at least in our preliminary work, we didn't aim to change the recommendation module. The only thing that we change is the input that we feed the recommendation module. So let's see this framework first. It's like we have, as we have done this before for the recommendation task, we have a user side, we have an item side, and we have the recommendation module. The thing that we want to investigate here in our work was that we want to change the item side. As see, we have this original content description, and we want to prompt large language models to generate different augmented text and concatenating this augmented text with the original content description. We aimed to investigate how well this framework can work. So motivated by all these observations, we propose 4 different prompting strategies. The first is we call basic prompting. It's simple. For example, here we have the description of an item is as follows, paraphrase it. So it is just ask large language models to paraphrase the original item description, which is here. This is the item description of a movie, which is Toy Story. And then we propose another prompting strategy, which we call the recommendation-driven prompting. The only difference between this prompt is from the basic prompting is that we add another instruction, which is, what else should I say if I want to recommend it to others? This is this is based on our intuition that, say you have a task to summarize a paragraph, and the first task instruction is summarize this paragraph, and then with the same paragraph, another task instruction would be summarize this paragraph so you can recommend it to others. So it is very like that human think about problem or try to summarize the paragraph. If we have an idea or a purpose in mind, then when we summarize it, we may focus on some specific aspects of the paragraph that we want to summarize. So this is the intuition that we have, and this is the prompting strategy that we propose. And the third prompting strategy is we call it engagement guided prompting, because as we have said before, we observe that there are mainly two sources of those incompleteness. First is that we may not fully understand the item that we want to recommend. And the second is that we may not fully understand the users that we want to recommend our products to. So to have or to model this user preference, we propose this engagement guided prompting, is that we want these engagement signals to guide large language models to better summarize the item properties that may be more valuable during the recommendation process. So here, the exact prompt would be summarize the commonalities among the following description. And the description is the description of the target item. And then it's the descriptions of other important neighborhoods. Here is a very simple diagram. We have user item co-engagement graph, and the edge just indicates the interaction. The idea here is that if we have this target item, then we want to use some importance matrix to find other important items, maybe this one, because these two items are co-engaged by a lot of same users. So we think that may guide the large language models to summarize the important properties that this item has. And the fourth prompting strategy was just trying to incorporate these both the recommendation driven and the engagement guided prompting, just adding this recommendation driven instruction, like what else should I say if I want to recommend it to others. And the second component is that summarize the similar or commonalities among the following descriptions. So these are the whole framework that we propose. Any questions so far?
Okay.
Okay. If no, I can keep going. Okay, sure. So how to evaluate the whole framework? The evaluation framework is like this, that we keep all the other parts consistent across all experiments. The only thing that we change is the parts that inside these dashed frames. Like we change different prompting strategy and we change the augmented text. And before we concatenate the augmented text and the original content description, we transform them or we encode them using the same text encoder. And another thing I want to say here is that we also tried concatenating the text first, then using the encoder, but we will show the experimental results later. But for most of the experiments, we just concatenated the embedded embeddings, not the original text. So here is the experiment that we did for different prompting strategies. I know it is there are a lot of different different abbreviation here, and let me explain them now. So the first thing first, let's take a look at this table first. So we evaluate our framework on two different data sets. The first is the movie lens 1 million data set, which is a well-known recommendation data set. And the second is the recipe data set. So the movie lens, the original movie lens data set, it only includes the title and the genre and all the other interaction of this inside this data set. It doesn't have item description. So we use large language models to generate the item description here. And for the recipe, they have description itself. So we just use the description that is inside the data set. And here are different prompting, the performances of the different prompting strategies. The different colors indicates different groups. So this darker blue here, it indicates the basic prompt. We have P tag and P infer. So what do they mean? Is to paraphrase. So this is this one, first one, the basic prompting. The description of anything is as follows. Please paraphrase it. This is the P-para. And the tag is the description of the items as follows. Summarize it with tag. So we want large language models to use tags to summarize the original item description. The third variant of this basic prompting is that we want large language models to infer some characteristics out of the original content description. So in this prompt variant, the exact example we use is that what kind of sentiment can this item description evoke? And the lighter blue here, which we have a rec superscript, this means that they are the recommendation-driven counterparts of their basic prompting. So all these.
I'm so sorry to interrupt. Hanjia, I'm so sorry. Your internet got
No
unstable,
problem.
and I think we didn't hear the very beginning. So can you just explain the three different colors that you're using? So if I
Oh,
understood
sure.
correctly, the dark blue is the basic prompting. The light blue
Yeah.
is, I'm so sorry to interrupt, but I think this is the
No.
important part. Please go ahead.
No, my bad. And you are definitely right. Let me know and I can re-explain it again. Yes, the dark blue here is the basic prompting. In our experiment, we implement three different variants. The first is P-para, is just ask large language model to paraphrase the original item description. And the P-tag is ask large language models to summarize the original content description with tags, so with hashtags. In other words, the generated text would be more brief, more short, and should have more summarized information. And the P-infer here is that we ask large language models to infer some characteristics out of the original content description. In our experiment, the exact example that we use is that we ask large language models to infer the sentiment of the item description. And the light blue here, which all of them has a rec as the superscript, they are the recommendation-driven counterparts of their basic prompting. So let's take a look at this recommendation-driven prompting again. The only difference between the recommendation-driven prompting and the basic prompting is by adding a recommendation-driven like instruction. Here is if I want to recommend it to others. So here, the recommendation-driven counterparts is just adding that simple sentence into those basic prompting here. I'm still good, right?
Yes, makes all total sense. Thank you.
Okay. And here, the PENG is the engagement guided prompting. And REC ENG is the recommendation driven plus engagement guided. So it's the fourth prompting strategy here. And as we can see here, this ablation study has showed that different prompting strategies shows augmenting the input text with responses generated by this large language model. They have inconsistent performance across two different data sets. We use these two data sets because they are representative. The movie lens, it represents the items that are well classified, like movies. The recipe, because inside this recipe data set, users, social media users, they can post their own recipes, and other social media users can choose to like or to like or comment on those recipes. So most of the items inside this recipe dataset, they are user generated. So unlike movies, they are less classified and more novel, more dynamic. And another thing I want to explain here is the horizontal blue line here. The horizontal blue line here is the performance of using the original content description. So the first observation here would be that by concatenating these augmented text, we have observed one consistent pattern is that concatenating these prompting, the text generated via these prompting strategies can all improve the framework that use the original content description. And all of them, they improved by a large margin here. That's the first observation. The second observation, I think I may jump the gun. I said it earlier, is that the performance across two different data sets may be inconsistent in terms of these prompting strategies. So we want to understand that how to explain these two observations. First is that why it can improve the original content description, and the second is that why they can be there can be varying performances across two different data sets across different prompting strategies. But before that, let's see another experiment that we have. So another experiment we have is that since we have different prompting strategies, so we have many different augmented texts. Then another thing that we tried is we try to concatenate the embeddings of all of those augmented texts. As we have seen before, we have 4 prompting strategies, and inside the basic prompting and the recommendation driven, we have 3 different variants. So by concatenating the embeddings of all of those generated text, we have this thing in the last row here. So here, the last row, LLM-Rec, is I can explain it from the first. It will be easier for us to understand. So the first is item popularity. It's not a learning framework. It just recommend based on how popular an item is inside of the dataset. And the second is that we encode the item description, and we use an embedding table to encode the user information. And then we use an MLP model to serve as the recommendation module. And the third and the fourth, the auto-INT and the DCNV2, they are more complex feature-based recommendation methods. And this LLM-Rec, it has the same structure as this MLP, the MLP baseline in the second row. The only difference between this MLP and this LLM-Rec is the input features. The input features to MLP is the original content description, but the input feature to LLM-Rec is the concatenation of all the augmented text and the original content description. And as we can see here, one consistent findings across 2 different data sets is that we have seen that LLM-Rec can empower simple MLP models to achieve superior recommendation performance, surpassing other feature-based recommendation methods. And this has many, we think this has many applications, because these more complex or more sophisticated feature-based recommendation methods, they are typically more difficult to train because they have a lot of different attention weights that need to be fine-tuned, and and also the combination of different hyperparameters are way more than simple MLP models. So this superior performance is one promising findings that we have observed in LLM-Rec framework. And moving on is that we want to understand, so what does this LLM-Rec prompting strategies have that help the simple MLP models to achieve better performance compared to the original content description? We try to understand or investigate this problem by looking at the recommendation-driven strategy and the engagement-guided strategy. So this is the first experiment that we have. It's about the recommendation-driven strategies. We want to know that what extra information does recommendation strategy driven strategy prompts LLMs to augment. And here we use a simple variant, which is the p-para and the p-para recommendation driven. The difference that between the p-para, the generated text of p-para and the generated text of p-para-rec are highlighted in blue. As we can see here, in the movie lens dataset, the different words that we didn't see in the p-para generated text is like thrillers, suspense, and mystery, exciting and thought-provoking, and others like classic, Back to Future, exciting plot, memorable characters, entertainment, classic action adventure. So so if you work on this movie lens dataset before, or you watched a lot of movies before, you would understand that the words that we find in the generated text of this p-para-rec are mostly related to some characteristics that can well characterize movie, the item movie. So in this example, you can see a lot of genre-related keywords inside this generated text of p-para-rec. And in this recipe dataset, you can see that deliciousness, a hit with everyone, easy to make. One thing I want to highlight here is that actually easy to make is a hashtag that is used a lot in this recipe dataset, although we didn't put it into the item description. But it's so easy to make. This idea is very similar to the genre. It's also a concept that can be used to characterize the recipe. And also like guests coming back for more, and flavorful, creamy, hit with your family and friends. So it's like a family foods or friends foods, or sometimes it's food that you can enjoy yourself. So a lot of different words here. The thing that I want to highlight here is that it appears, or it occurs to us that the recommendation-driven strategy helps large language models to augment some information that is that can be used to characterize the items. And these characteristics, they are highly correlated with the characteristics that we use in recommendation task. Because say, if you want to watch a movie, before you using the browser, you may think of the genre that you like a lot, or you watched more frequently. Then you go into that genre, then you search for some movies. So it is here is that we see that our recommendation-driven strategy elicit LLMs understanding of the items. In another word, that it seems that LLM understand the properties that are more useful in recommending movies or recipes. Then it generated words that are related to that. So to evaluate this observation, we did we generated two different augmented texts. One is we call the p-para keyword, and one is we call the p-para mask. So how do we come up with these two variants? So the p-para keyword is that, as you can see here, the keywords in the movie lens is more like genre-related words, and the words in this recipe are more like these like easy to make or deliciousness, these things. So the p-para keyword is that we use the p-para as the base, and as long as there is a word that is related with Java, then we and also appear in p-para-rec, then we inject it into the p-para generated text. Okay, that's a very long sentence. Let me give you one simple example. So here, say if we want to construct the p-para keyword of this first example, then it would be the p-para keyword is the p-para. Then we inject the words that appear in this p-para-rec and which are also Java related. So we will inject these thrillers, we will inject mystery into the p-para. Then we call it p-para keywords. So the second example would be using this p-para as the base. Then we inject classic, we inject entertainment into this p-para. And for the last example, it would be using this p-para as the base, and we inject classic action adventure into this one, and we call it a p-para keyword. And as we have seen here, is that not instead of putting all these augmented text into this p-para, only by injecting these useful keywords, we also observe an improvement in the recommendation performance. And for the recipe, it's the same. But what is this p-para mask? It's using the p-para-rec as the base. Then we mask out the words that didn't appear in this p-para generated text. Ideally, it would be masking out this thriller, suspense and mystery, exciting and thought-provoking. That's an ideal case. But it is first, it was difficult to implement at that time, and we want to see see how it works sooner. So what we did was more like rule-based. As long as the word doesn't appear in this p-para but appear in this p-para-rec, then we just mask it. And we have seen that we observed a decrease in the recommendation performance as long as we mask out those words in the p-para-rec. And here are some more examples in the
Sorry,
p-tag.
before you move on, I'm so
sure.
sorry, just to make sure I understood, because there's a little bit of a delay when you move your mouse. So I think it will be helpful just to make sure that I follow. Hopefully other people will also jump in with their questions. Would you mind going back one slide just for a second?
One slide, okay.
Because right now we see your description slide.
Let's see. You see the you want to look at
the para slide, because I think I was trying to understand what you meant by the keywords. So if I understood correctly, what you were saying was that in using you were comparing the two different augmentation strategies, and you could see that in rec it was using more abstract keywords. And so what you did was you put those keywords back into the original paraphrasing, and you wanted to see if that improved the performance. Did I understand correctly? Okay, okay, that makes sense. Thank you so much. I'm sorry to interrupt.
No. Actually, this kind of interaction is really good for the presentation. So I know that this part may need more explanation or interpretation, but really, thank you.
No, it makes a lot of sense. Okay, so you were showing us the example. Please feel free to continue. Thank you.
Okay. And here are some more examples of the p-tag variant. Here you can see it more clearly because all these information are now more concise because they are summarized in hashtags. And you can see that there are some different hashtags that only appear in the p-tag rec, but doesn't appear in p-tag. And these hashtags, they are more Java related in the movie lens dataset. But for the recipe dataset, as you can see that Oh, another thing that I want to highlight here now is that as you can see that there is some inconsistent improvement in the previous figure, that we have seen different prompting strategy, they perform differently in these two data sets. This is one thing that I want to highlight and may have a lot of potential for future work, is that, as you can see, the recipe is relatively less classified, or more novel or more dynamic, because LLM itself may not have a well understanding of this recipe item itself. So it doesn't generate good enough hashtags or abstract words that can better characterize this item. That's one hypothesis. And this is another example showing the p-infer and the p-infer-rec. One thing that we observed in this variant is that the performance may depend on how good the inference itself is, because this prompting strategy is asking large language models to infer some characteristics out of the original item description. Say, we want to know what sentiment does this item description evoke. But say if the sentiment it inferred is not correct, then the performance may not be good as well. That's also one small observation of this variant. And now we can take a look at the different words that generated by this engagement guided strategy. Here is that we compare the p-engage with the original content description. As we can see here, the example shows some words like resilience, hope, friendship, inspiring, adversity, friendship, humorous, entertaining, like urgency, suspense, exciting, thrilling. It is different from what you have seen in that recommendation-driven strategy. One impression is that it has fewer words that are related to genre, but more words that you can observe from the description of the target item and the description of other important items. So this is more like a reasoning process or summarizing process of LLM, that we show LLM that, say, these item descriptions, they should share some commonalities, and ask it to summarize it. And the generated text here is more like the summarization of all these item descriptions. So to put it in another word, was that if the recommendation-driven strategy is trying to prompt LLM to augment some text based on its own understanding of the general about this item in a general way, then this engagement guided strategy would be using LLM to prompt the text which is more personalized, because for each target item, the important neighborhoods are gathered, or the important neighborhoods are different. So for each item, it will have a personalized prompts, and the generated text would also be different based on how the engagement graph looks like. Oh, and I just realized that I didn't say what methods that we use to find these important neighborhoods. So in that item user bipartite graph, we use PPR to calculate the relatively importance between two different items. And we use that as a metric to measure how important the items are to the target items. But actually, different ways can be implemented here. It doesn't have to be limited to PPR. And one more interesting that we have found here is that the effect of concatenation. I have highlighted this concatenation at the beginning, as we have shown that by concatenating the embeddings of all these generated text, we have observed a superior performance. And the horizontal blue line is the MLP model with the original content description, but the red line here is the DCNV2, which is a more complex and a more advanced feature-based recommendation methods. As we can see that in general, concatenating more augmented text can improve the performance of the original recommendation even more. And by concatenating all the information together, we have the optimal performance compared to other baselines. And also, I want to highlight here is that we tried to, so this is the concatenation of the embeddings. So we also try to concatenate the text, then feed it into the encoders. We didn't see optimal performance or optimal improvement with that variant. So to implement, oh, sorry. Are you there? A question? Okay. Yes. Yeah. So the findings that we've seen here is that concatenating the embeddings is more effective. And that's it. That's mostly the whole story of the framework. And most of these, all of these experiments, they are implemented using the GPT. The augmented text were generated by GPT-3, and we have also experimented with Llama 2. The pattern are the same. The only thing is that maybe the augmented text, the quality of the augmented text of Llama 2 is not better than the augmented text of GPT-3, but the overall pattern is the same, that we have observed the superior performance of the concatenation, and we also seen that it can improve the simple MLP model. So that's it. I'm ready for questions.